Hey everyone, Joey here. I'm out here in Los Gatos doing a little dry cleaner soil vapor job. So I want to take a minute and just kind of show you all how this works. I'm right outside down gradient of this dry cleaning establishment, and we've got some vapor wells that we put in previously. I'll show you right here. Got two wells here. We got we got a 15-footer and we've got a 5-footer, so a shallow and a deep well. Groundwater here is about 40 feet, give or take. So these basically are showing us anything that's off-gassing off the ground vapor or the groundwater, and also anything that is basically right beneath the slab outside of this building here. So I've got my kit here, and basically I'll show you how this works. Okay, so this is our basic setup. I've got everything plugged in here. I've got the 15-foot well attached, and what this is it's a 2-inch diameter borehole that goes down to 15 feet. In the center of that runs this Teflon tubing. That tubing at the end, at the 15-foot mark, has a little plastic filter to keep silt from running into the sample can here. That filter, at the bottom of the hole, there's a 1/2 foot of sand, and then the filter, and then another 1/2 foot of sand. So there's a 1-foot sand pack that allows the filter to not get gummed up with silt or anything in the overlying or the strata that it's placed in. And then above that is bentonite clay, all the way up to the 5-foot sample, which is this one right here, and then another foot of sand pack with a probe put in the middle of it, and then more bentonite all the way up to the surface, and then we seal it off with a well cap and concrete to make sure no water or anything gets in there. Thank you. So we've got this. Someone just brought me coffee. So we've got this set up. This is our flow controller. This makes sure that the can fills at 150 milliliters per minute. It gives us a nice slow flow, so we can be sure that we're not going to overstress the soil strata, soil gas. And basically, if you overstress it, if you pull too fast, you put the system out of equilibrium, which will force more contaminants into the vapor phase. Anything that's adsorbed onto particles and things like that will, it's an equilibrium. There's a dynamic equilibrium down there. If we pull too fast, we put things out of equilibrium, and they'll go towards equilibrium. So we'll basically skew our results. So the way this is set up, we've got right here, we've got our purge port and a purge can. This can will just pull whatever air is in this tube, so that we can be sure that we're not sampling air that's in the well itself. We'll be sampling the air that is just in the strata. We've got our helium can here that we're gonna put a plastic sheet over the top and charge this whole shroud with helium. We've got a helium meter right here. This will read and make sure that we have a 20% helium atmosphere inside the shroud. And this is just a little air pump that will just make sure that the helium and air is circulating in here, so we don't have a high concentration over here and no concentration over here. Let's see. So the importance of the helium, what that does is it allows us to basically do a check to make sure that we don't have any leaks in the manifold or any of the connections here. You can see there's a lot of little connections that go all along this thing. It also lets us know that where our well goes into the ground, it lets us know that it's not sort of short-circuiting. It lets us know that the air from the ambient air, it lets us know there's the seal is secure, and we're not pulling in air from above that would alter our results. Because we only want to sample, we only want air getting into this can from the strata, from the interval that we're interested in. So in this case, it's 15 feet and 5 feet. 15 feet and 5 feet. So basically, by charging this with helium, purging out the line, and sampling the helium, we can tell that, you know, if we get this can back and there's helium in it, we know that we had a breakthrough somewhere, and we know that these sample results are not valid for this purpose. Another little check we have on ourselves is what we call a shut-in test. So basically I shut off the valves on either end here and here, and completely isolate the manifold to the can. Then I open up the can, and you can see that the can pressure is -30, so this is a fully charged can. This is good to go. Then you can see that the pressure over here, which is our quote-unquote borehole pressure, is close to 30, which is because this is closed off, this is the pressure that's being exerted by the can. So because these are both relatively the same and they're both holding steady, we know that this manifold has no leaks in it. So when we charge this system with helium and we pull in a sample, we know that we're not going to have any breakthrough related to the manifold itself. Okay, so here's what it looks like all set up. I've got my helium meter on, I've got my pump on, I've got my shroud cover in here. Everything's the same as it was, it's just covered with this plastic. So now if I open up my helium tank, you should be able to see so I fill that up, and now if we pull with this helium, you can see that within the chamber, there's a 42% atmosphere of helium in there. So that lets us know that our shroud is sufficiently charged with helium. So if there's any helium in our sample, we'll know that those sample results were pulling. There was a breakthrough somewhere in the system, and we weren't pulling from the underground strata that we were targeting. We were pulling in some ambient air, either through the manifold, through one of the connections, or there was a short circuit basically from the surface down to the sample tip, which is rare in these cases. That's more of a concern with a subslab vapor pin or soil vapor probe, because that's just going through the 4 inches of concrete and then just sticking under the surface. So that's a bigger deal, bigger concern in the subslab application. With these deeper wells, it's not really a concern because the probe is under 5 or 15 feet of bentonite clay, which is hydrated, sucks up all the water and fills up that borehole space. But basically what I'll do here now that I've charged the shroud, I'll turn on this purge can and I'll purge the line, and while I'm purging, I keep track of the helium content, the time, and this is how many milliliters I purged out of the well. And then once that's done, I'll switch on my can, and I'll basically go 29, 25, 20, 15, and I'll sample until the can is at -5 pressure, and I'll record the helium in the shroud the entire time. So that way, if there's any helium in there, we can look at the concentration the concentration in the shroud, and we can calculate a breakthrough. So our results won't have to be thrown out necessarily. We can just say, oh, these are skewed slightly high by a percentage or a dilution factor of this much. So when we hook this up and open the valve, it just starts pulling in. It just starts pulling in air. If the formation is too tight, this doesn't have enough suction to pull that air out, which becomes problematic with tight formations. But since this is low, we're all good. We can see the can is running down relatively smoothly, relatively quickly. Looks like my helium is down a little bit, so I'm going to charge it with a little more. And take my next reading.